Alright, let's talk about high and low pass filters. These are circuits that can be made with just a resistor and a capacitor, and they allow us to control what frequencies can enter a circuit that we build. We can only allow a certain band pass through. So let's just start with a low pass filter. And before I draw the circuit, I'm going to kind of draw a function of what it does. So I'm going to, instead of time, this axis is usually time, but I'm going to make it frequency. And this will be the voltage. Let's say the output voltage from a low pass filter. This is 0 hertz, and this is, I don't know, infinity hertz, or some super high frequency, okay? And with a low pass filter at low frequencies, or even at 0 DC, the voltage will be at, it'll be its full value, and once it hits some cutoff value, it will no longer pass that frequency, and it will start this downgrade and kind of, alright? We call that a low pass because it passes low frequency signals. And we use this for selecting the signal that we want, and like filtering out other things, because anything other than the signal we want is noise. If this low pass filter was set to cut off at 10 hertz because maybe it's a heart rate sensor, and 10 hertz is probably the highest you probably never will even see 10 hertz on humans. But if you have 60 hertz somewhere way out here, we don't want any of that 60 hertz to mess with our circuit, so we'll build a low pass filter, and we won't even mess with any of that stuff. Alright, on the other hand, if you're building an audio circuit, like an amplifier, we want to do the opposite, right? Audio frequency is, I don't know, between 20 hertz to 20,000. Most people can't hear to 20,000. I know I can't, but just as a general rule of thumb, we say 20 to 20,000 hertz is the audio bandwidth. In this case, if I call this line 20 hertz, anything less than 20 hertz, we want it to ignore. So instead, our curve should pass higher frequency signals. Call that a high pass. And if you combine a high pass and a low pass, you can establish a band pass. So if we wanted it to stop at 20 kilohertz, we would create a low pass filter that would then block everything after 20,000 kilohertz. So, ultrasound would be somewhere out here, and AM radio and FM radio, all those things that are a lot higher than 20,000 kilohertz will not be able to pass through the circuit. So let's design a low pass, since that's the first one I talked about. We start with a alternating voltage and AC source, and we have just one resistor, and then we have a capacitor going to ground. And you would take the output voltage here V out. So as you can imagine, as the frequency of this guy increases, the reactive impedance of this capacitor is going to drop, and it will more and more short that signal to ground. So the higher the frequency, the more the signal is getting shorted to ground or not passed. At low frequencies or even DC, remember if this is a DC circuit, we're going to treat the capacitor as a short, or sorry, as a, it'll be treated as it's open, and then we'll get the full signal coming out. And we can characterize this with some math. The first thing to keep in mind is the capacitive reactance. X of C is equal to, we do 2 pi times the input frequency times the capacitance, and then invert it. That is the impedance at a given frequency. And we see we actually have a voltage divider created here. And voltage divider is V out equals Vn times R. If this were a voltage divider with 2 resistors, that would be R2, you know, over R1 plus R2. Now, we can't just say R1 plus R2 because the reactive impedance is actually at negative 90 degrees, so it's a vector. And we have to add it a little bit differently. It comes out almost the same. V out is equal to V in times, instead of R2, it'll be X of C divided by, and we just take the vector sum of R1 squared plus X of C squared. And that will be our output voltage. Let's throw some numbers in here. Let's say this is 1 kilohertz, or 1 kilo ohm. This is 1 kilohertz. At 5 volts peak to peak, we'll say 5 volts. And our capacitor is a 0.1 microfarad. So our X of C, if we want to calculate that, should be 2 pi times 1 kilohertz times 100 nanofarads. And I have, oh, I think I messed up here. 2 times. Okay. Yeah. This is equal to 1.59, we'll say 1.6 kilo ohms. And this is a 1K, so we'll see how that creates a voltage divider. And let's calculate what our V out is. I'm just going to square that, add it to 1,000 squared, take the square root, invert it, and multiply by 1592. Okay, so this portion right here, that is equal to 0.847. So 0.847 or 84.7% of 5 volts is equal to 4.23. So, you know, if we're going to answer our question, does this circuit pass a 1 kilohertz 5 volt peak to peak signal? I mean, at first it's not obvious because we're getting a voltage out. The circuit doesn't, you know, it's not exactly, you'll notice even on the graph that I drew, if I go back one page, it's not a hard cutoff, right? It'll reach a certain point where the voltage output voltage will start to drop, but even then, it'll never actually hit 0. So what we say is that if the output voltage, if V out is less than V in over the square root of 2, or if V out is less than 0.707 times V in, if it's that much lower, then we say it has hit the corner frequency, and everything after that is just going to be cutting that voltage off. So 0.707 is the square root of 2. 2 take the square root, well, it's 1 over the square root of 2. And if we compare 0.707 with 0.847, we see that 4.23 volts from this circuit is actually above our cutoff, our corner. And so yes, the answer is this circuit will pass a 1 kilohertz signal. And I do have this built on the scope, so now's a good time to check this out. I've got my frequency or signal generator set to 1 kilohertz. You can see on the scope that I have channel 1, which is yellow, hooked up to the input voltage, and the blue is channel 2, that's the output. You can see two things. One, the output is a smaller amplitude than input, and also it's phase shifted, and the phase shift is caused by the capacitor. Let's put this thing at our calculated corner frequency, which was 1590. Alright. And we can see the output is 3.48 volts, which if we take 5 times 0.707, the theoretical value is 3.54, and that's pretty close. I guess the next thing we can do is, let's see what happens whenever we change our frequency. So this is a low pass filter. We should expect the blue amplitude to get really small when we increase the frequency. So I'm also going to have to simultaneously adjust the scope scale. Oh. Let's see. Oh, and I'm even. Let's see. Actually, and it looks like. Oh, you know what? I just realized. The circuit I have built here is a high-pass filter. I was playing with. They're very similar. You'll see in a second. Oh my! So here, yeah. Let's go back to our corner frequency. All right, we're at corner frequency, and from this point, as we increase the frequency, did I not even switch? Oh, that's funny. I pulled them out and put them in the same place. We want the capacitor going to ground so it can short out high frequency signals, and the resistor goes across. Fair enough. There we go. As I bring that frequency up, the output voltage, the blue line, is approaching 0, a flat line, and I could even put this thing at like 10 hertz. It's going to be really hard on the oscilloscope. So, yeah, but you can see that both lines are overlapping, so we're getting the full input voltage coming out whenever we approach 0 hertz. So just real quick, I'm going to do high pass, which behaves intuitively the opposite. So on a high pass, instead, the capacitor is in series with the power supply, and the resistor is what goes to ground. Exactly the opposite. High frequencies will pass easily through the cap, and at low frequencies, the capacitor will block, of course, and we take the output voltage. Here, the math is the same. And, oh, you know what? If you want to calculate the corner frequency for a circuit, did I do that on the last one? I think no, we just calculated the impedance of the capacitor. The corner frequency is, it's actually similar to the capacitive reactance equation. The corner frequency is 2 pi R times C, and then take an inverse. So and this is for high and low pass filters, it's just that whenever you hit the corner frequency, for a low pass, as you go above corner, the voltage drops off, but for a high pass, as you go above the corner frequency, the voltage approaches the input voltage. It increases. Okay, so for the last one, it came out to be 1.592 kilohertz, which interestingly was like the same value of the capacitive reactance, just because of the values I selected. Won't happen every time. And that's what it'll be for this one, because R and C haven't changed, just their order in the circuit. So just let's do another example. FC is equal to, let's pick, well, you know what? Let's say you knew what the corner frequency you wanted was, like 20 hertz. And we want to do a high pass filter on this and cut out everything below 20 hertz. So in this case, we would rearrange the equation with whichever value you were going to be changing. So I'd say probably R, I don't know, we'll go with R, as since I have a bunch of resistors, you know. R equals 2 pi FC times C. All I did was swap the positions of R and FC. And now, assuming I still have my 100 nanofarad e to the negative 9 times 20 hertz times 2 times pi, and it looks like I need a 7 or a 80K resistor on that. Okay, and then you could imagine doing the same thing for, if we were doing audio, 20 hertz to 20 kilohertz, you would just do the same thing again, except use 20 kilohertz here and build a low pass filter. And the last thing I will show you is, I guess, what you already saw when if I put these components in the other order. So capacitor goes from input to output, and a resistor goes to ground. Alright, we'll hit the corner frequency again. And, okay. So it looks the same at the corner frequency for both circuits, but the difference is, as I increase the frequency here, since it's a high pass, the output is approaching the input. and by the time I get to about 10 kilohertz, you know, it's becoming hard to tell. Here I am at, here, let's put this at about 50 kilohertz. I mean, they're right on top of each other. All right, well, I hope you learned something. I personally think high and low pass filters are really cool because of how simple the componentry involved is. And if you have any questions, feel free to ask them in the comments. If you like this video, feel free to subscribe. Thanks for watching.